I'm going to talk about Thevenin's theorem this evening, and we're going to discuss the fact that Thevenin's theorem states that any two terminal networks can be replaced by an equivalent circuit comprising a constant voltage source in series with a single resistor. So in the case of the diagram on the right hand side, we have a constant voltage source denoted by the circle, and that's in series with a single resistor. And the point in Thevenin's theorem is that we have this voltage source, which is referred to as the Thevenin voltage VTH, and the series resistor being the resistor RTH. So this idea of an equivalent source comes from this concept here, meaning equates to rather than equals, equivalent to, beg your pardon, rather than equals. And it's any network. It's probably a wee bit easier if we actually went to an example. But first of all, the concept of constant voltage source is actually discussed in another video that I've created. Okay, there's a link in the description, and well, if I can figure out how to do it, I'll put a little box up so you can click on it, etc. But in the other video, we talk about this idea of constant voltage source, which refers to this in series with a load, and then under no load conditions and load conditions. So go check it out, and it will maybe make a lot more sense once you look at it. So applying Thevenin's theorem requires a few steps. Okay, so there's only 3 of them at the moment. The first step is remove the resistor that you want to know more information about, voltage and current, etc. Okay, and we then calculate the Thevenin voltage and resistance. Then finally, we replace our circuit with that equivalent circuit. So something similar to what you saw here. Now, it's probably easier to just actually look at a worked example. So we'll go ahead and take a look at this. The question that is being put in front of you is to use Thevenin's theorem to calculate what the voltage drop is across the 6 ohm resistor. What is the voltage drop across the 6 ohm resistor? Now, if we take a look at the steps that we've got to apply, this goes right the way back to this. Remove the resistor in question. Okay, so take away the resistor that we want to know about. In the case of Thevenin, we remove it and we replace it with an open circuit. So we've taken the resistor away and we've not replaced anything. There's no other connection there. I've named my terminals where the resistor was connected as terminals A and B. So now that we've done that, what we can do is we can start to look at the nature of this circuit. That being, we have an 8-volt series of cells, and those are connected to these 3 resistors in this particular example. We have a resistor 10 ohms, which is in series with 2 resistors 15 and 4 ohms, which are in parallel. And what I like to teach my students is that, well, how do we understand the concept of which one's in series and which one's in parallel? If we think about what the current does, the current will flow out of the cell in terms of conventional current theory, and it will go around the circuit and flow back into the circuit, into the cell. So given that we know that, we know then that the current is going to flow out of the cell, and the only way it can go is through the 10 ohm resistor, which means that the 10 ohm resistor is in series, and then it will, let's remove that, didn't mean to go around like that, it will flow around the circuit this way. Now, why does it do that, and why does it ignore the 4 ohm resistor? The fact is, the 4 ohm resistor doesn't have a connection between A and B. Therefore, the 4 ohm resistor does not experience a current flow. So I'll make a bit more sense of that in just a wee second, I suppose. So let's take a look at what the battery current is, because we need to understand what the battery current is going to be doing. And I'm going to show you 2 ways of doing this. So there's 2 ways of understanding this particular problem. The first one is we can look at simply the current relating to the battery current, and then the Ohm's law equation. What is it that we're trying to work out? We're trying to work out the voltage across these 2 terminals. So the battery current, and I'll call this I bat, that's going to be Ohm's law 8 over 10 plus 15. What's happening here? A reminder. The current is flowing out of the battery's positive terminal through the 10 ohm resistor and through the 15 ohm resistor back into the battery. No current is flowing through the 4 ohms because there is no connection between A and B. So it's literally just the application of Ohm's law right now. And what we get is that the battery current is going to be equal to 0.32 amps. From here, we can go ahead and work out the Thevenin voltage. So, if I didn't say it earlier on, in fact I know I didn't say it earlier on, remove the 6 ohm resistor and calculate the Thevenin voltage. We are on our way to doing that. So to calculate the Thevenin voltage, VTH is going to be 0.32 times 15. Now, at this point, I know that some of you might be thinking, where did 15 come from? Here is the caveat. The voltage across the terminals A and B is the exact same voltage across the 15 ohm resistor, meaning that they're parallel. So VTH, in this case, is going to be the same. And the reason for that is because no current flows through here, so this voltage measured here is going to be the exact same as the voltage measured across these 2 points. We're just looking at the parallel nature of the terminals A and B and the parallel nature here. And that's because there is no current flowing through the 4 ohm resistor. Now, for some of you might be thinking, well, why can't we just use the voltage division rule? This is the other way of doing it. So I'm going to put a little line through that. We could have taken the voltage division rule, and we could have taken the supply, which is 8 volts, and we could have multiplied it by 15 over 10 plus 15. And it gives us the same answer. To understand what the voltage division rule does, it takes a ratio of the split across 2 resistors, the voltage across, I'll make that the same colour, the voltage drop across the 10 ohm resistor, and the voltage across the aforementioned 15 ohm resistor. And that's it. So we've now calculated the Thevenin voltage. Let's take a look now at step 2. Now that we've calculated the Thevenin voltage, we can now calculate the Thevenin resistance. And the steps to this procedure is we need to replace the 8 volt battery with its short circuit, in other words 0 ohms. So as you can see beforehand, we had an 8 volt cell. We assume the internal resistance to be 0 ohms in the case of our theoretical example. And then from there, what we do is we take a look at the resistance, we take a look at the resistance from the perspective of the terminals A and B. In other words, it's as if we're looking from these two terminals, looking this way. That's meant to be a picture of an eyeball. You may or may not see that as an eyeball, I don't really know, but it's meant to be looking at that perspective right there. Ooh, that's not meant to be white. From that perspective. So, the way that I like to teach this particular fact is if we think about what an electron would do if it was traveling from here around to B. So from terminal A to B, well, we can simply consider that as being the series resistance here, 4, plus then the split between the 10 ohm and the 15 ohm. So the current moving from A to B is going to get to this node. Some is going to go this way, and some is going to go that way. And then it's all going to rejoin at this other node. So from that we can get 4, our series resistance, plus then the product over sum. 10 times 15 over 10 plus 15. And that gives us a Thevenin resistance of 10 ohms. So now we have the Thevenin voltage, 4.8 volts, and the Thevenin resistance equal to 10 ohms. Really dodgy looking ohm symbol there. Ohms, there we go, omega. Have we done everything we need to do at this moment in time? Yes, for now at least. We have built up an understanding of VTH and RTH. The final part, and this is something that I stress to all of my students, is always draw your equivalent circuit. Okay, it's the same for almost any area in electrical engineering. If you're network reducing, draw your network reduced circuit as you go. It leads to less confusion. It makes it much easier to understand what's going on. So the Thevenin equivalent circuit, as shown here, is now showing us the Thevenin voltage that we've calculated and the Thevenin resistance. And then we'll replace the 6 ohm resistor, the very resistor that we were actually interested in, back into our circuit. Okay, remembering that what the question was actually asking, calculate the voltage across the 6 ohm resistor. So thinking about what is going to be the voltage drop across this chap right here, 6 ohms. The point of drawing the equivalent circuit means that we can actually understand what is going on. We can take a look at our equation that we need to build, and it's going to be a voltage division equation. So we're going to take our Thevenin voltage and we're going to multiply it by the resistor in question over the sum of the series resistances. And that's going to give us an answer of 1.8 volts. And that is Thevenin.